Okay, I think we're ready to start. So thank you for coming. Before we start with our main presentation, many of you don't get to see Professor Charles Norkey from the law school. He's a member of our institute, and he's coming because he was chauffeuring Professor Lynch. So Professor Amanda Lynch, as you will note in a couple of moments, is from Australia. She's the Lindeman Professor at Brown University, and even, I think more notably, is the chair of the research board for the World Meteorological Organization. So she ends up going to Geneva several times a year, obviously. She has her undergraduate from Monash University in Australia and University of Melbourne for her PhD. And then you went to get a master's at Brown University, which is probably an interesting story. She has tons of professional experience. She's worked all over the place. I'll start in the early years. She was a meteorologist with the Bureau of Meteorology in Australia. She's been a postdoc and a faculty member at the University of Glasgow. She was a professor and a member of series and other things at University of Colorado. And now that since she's been at Brown, she started the it's the Institute at Brown for Environment and Society. So she has quite an amazing career in terms of traveling around, getting experience. She has tons of honors, a whole bunch here. Let's see, the Priestley Medal, which is a very big deal from the Australian Meteorological and Oceanographic Society. She's a member of the Australian Academy of Technological Sciences, American Meteorological Society, and Presidential Fellow for Brown University and many others. She's worked in a lot of different venues, including for the World Bank, for the Australian Community Climate and Earth System Simulator Program, Commissioner for Environmental Sustainability, Victoria, Australia, Los Alamos National Laboratory. Tons of books, two that come to mind in particular. One of them, which Jacqueline probably knows, is called Urgency in the Anthropocene. And the other one was done in 2006, Applied Atmospheric Dynamics. Tons of publications. And what she's going to talk about today is extremely important. It's not only about the science in the Arctic, but also about how policy and the law interact. And ideally, will give us some idea of, as it says here, what the trajectories might be, although they probably changed since the first time you made this slide.
Right, so, exactly, yeah.
So with great pleasure, I'd like to introduce Professor Lynch.
Thank you. Thanks very much, Paul. Very generous. So, and I'm really pleased to be up here. This is actually only my second or third time in Orono, and I really love being up here. It actually does give me a lot of memories from living in Alaska, which is one of my favorite places in the world. So what I'm going to be doing today is to talk a bit about some kind of use cases for developing scientific information in ways that it can directly inform policy or decisions. And this is all part of a project I've been running. It's been part of the Navigating the New Arctic initiative, which I know many of you have been involved in, from NSF, that's since sunsetted, but you know, the projects are still ongoing. This one's called Converging Pressures in Arctic Development, and it's a consortium of, I think, 11 universities, and at Brown we're the lead university. And so there's a lot of different things going on, and feel free to visit the website to find out what's going on. But I'm just going to give you 3 examples of work that I was directly involved with that speaks specifically to this connection between climate science and the decision space. If I can make this work, there we go. So as we know, climate change is amplified in the Arctic, and I'm sure everyone here is well aware of that. And so that amplification is apparent in a lot of the signals that we look for climate change. And this has been true, you know, since I've been working in the Arctic almost 30 years, working with decision makers in the Arctic, you never had to argue the climate change point because they could see it. And so that made it an excellent testbed for developing these ideas over time, because all of these changes are having impacts on decisions and have been for several decades. But of course, now as we're getting an acceleration of those geophysical indicators of change, that engendered, particularly in the 2010s, this idea of the race to the north, the idea that this was an opportunity and that opportunity needed to be realised, whether it was in the exploitation of renewable and non-renewable resources, so everything from fisheries to oil and gas, or if it was claims for jurisdiction over various parts of the Arctic Ocean, whether it be the surface oceans or the continental shelf. And indeed, with that came anxiety that led to an expansion of military installations around the Arctic for all of the Arctic nations, but particularly Russia. And so Russia went through a massive expansion of their presence along the edge of the Arctic Ocean on their side of the Arctic. And part of that, of course, is driven by the fact that the sea ice, as it retreats, is evacuating preferentially from the Russian side and piling up in the Canadian archipelago. And so all of that led to this general idea of a sense of opportunity. But then as that race to the north idea started to take hold, almost at the same time, questions about this started to come up of, well, you know, exactly what kind of opportunity is this, for whom, under what circumstances, and what in fact are the real limitations. And that's where you start to get into the decision space, where an individual decision or policy or claim becomes much more complex and nuanced when you come down to the particulars. And that's what we're trying to do in CPAD, is to develop the kind of the knowledge foundation for being able to engage with those kinds of questions. So I'm going to talk about three particular issues where we have a very clear signal in the geophysical system, and thinking about the decisions that are being influenced. So sea ice retreat, snow, and then permafrost. So, and it's all of this work is motivated by this idea of what scientific knowledge is useful and used in any particular situation. So for sea ice, the particular use case is maritime operations. It was really this and some papers that came out around 2010, 2011 on new routes through the Arctic. You know, the sea ice will retreat, and then all of a sudden, you know, everyone will be shipping across the top of the Arctic Ocean. And that was really that impetus for that race to the north idea. And so what we want to look at, and a lot of this work was with my postdoc, Shweka Lee, and with Charles Norkey, who's here, to think about exactly what we can know, because what we saw in those early kind of climate model scenarios was there was a real lack of nuance about exactly what about the ice was affecting the ships, how uncertain we were of the different elements of the trajectories that would affect those routes, and then what decisions were being made on a day-to-day basis. And so the way that you can do this, and we tried to model for our partners, particularly in operations, a kind of best practice for using climate scenarios, which means you have multi-model scenarios. You often have multiple realizations of all of the different climate models, and then you're considering different scenarios and where they depart from each other. And so this one is just showing One of the scenarios, so this is SSP 370 for anyone who's involved in IPCC, that these different future scenarios of climate change have different labels. This is kind of the middle of the road one. We selected 16 of the models that were deemed best by CMIP, the CI Model Intercomparison Project, looked at the climate models that did the best job of sea ice in the 20th century. Based on observations, we selected those 16 and extracted those scenarios for heading into the future. As you can see, there is a massive spread. So even if they are all kind of locking in on what happened in the 20th century, the 21st century still has large, a large spread among models. And of course, there is no one best model. So you couldn't pick one model that was perhaps doing the best in one thing or another and say that's the trajectory we picked. There's no basis for that. And then, of course, the other thing which is really critical, and people who operate in the Arctic know this, is interannual variability is huge in the Arctic. And so if you're making infrastructure decisions and planning decisions for investing in ships and moving your material around ports, you need to have some lead time, and interannual variability starts to hit you. And so when you look at these, so for example, the year and 90-day shipping season, which we were told by the operators at Maersk was a good solid amount of time that would make it worthwhile. But then the year you achieve that season for the first time in these scenarios, you know, some of them are saying we've got them already, which we don't. And some of them are saying we never get them. So there's not a lot of guidance here. And so what we wanted to then look at was, well, okay, so you have these papers that came out in 2010, 2011 said, you're going to have access by this date. And then you look at the data and you say, well, no, you can't say that. So what scientific information is actually useful? And so one of the ways we started getting into this was to look at the cost of getting it wrong. So if you decided to make investments based on one of these scenarios, what would it cost you if you got it wrong? And for that, we worked with a finance professor from Babson College, and he did some cost modelling for this using different methodologies, all based around the Black-Scholes option pricing model. And one of the things that we could do with this is look at the difference between the ensemble mean of all of the cost curves associated with every scenario compared to the cost curve of the ensemble mean of the models, which is what those financial projections usually use. And in fact, it's the guidance IPCC gives is you've got a lot of models, there's a lot of spread, the ensemble mean is the most defensible scenario to use. But if you do that, so this is the ensemble mean cost curve, and this is the mean cost curve of the ensemble, and you can see there's a big difference in cost. So this is the cost on this axis, and on this axis, this is when the shipping season gives you the amount of time you need, and below 1 is when the shipping season is not long enough. That is, it's icing up too early or the ice is getting too late. And so this is where you have the cost. So there's a big spread depending on how you actually just construct what your averages should be. And so using a multi-model ensemble mean underestimates the variance that the operator should assume. And so that was useful insight for them. What we also found was that the uncertainty in the interannual variability, which is part of what gives you this slope, that uncertainty weighs more than the uncertainty in across the different models. And so actually nailing the interannual variability for the operators turned out to be the information that we needed to focus on. They were less interested in the uncertainty amongst different models. I'm much more interested in the uncertainty that the different models presented on what the interannual variability was going to be. So that's one kind of example. The other issue, which actually arose out of an idle question that I asked Charles one time of, well, we know the ice is evacuating over the Russian jurisdiction preferentially compared to the rest of the Arctic. What does that mean for navigation? And that engendered a whole lot of research. As it turned out, it was a complicated question. And it all comes into focus with this article from the United Nations Convention on the Law of the Sea, which governs the jurisdiction of various zones in the Arctic. And Article 234 was negotiated as part of that convention, and this was in the late 70s, and it was signed in, what, 82? This article was actually drafted between Canada and Russia, who at the time, you know, they were not allies by any means. This was during the Cold War, but they had a shared interest in the governance of ice-covered waters. And so between those two country negotiators, they came up with this text. It caused some consternation in the US delegation in some cables that Charles was able to unearth. That led to a kind of a very scrambled negotiation so that the text we have is the outcome of that kind of push-pull. What I love as an ice modeler is how incredibly fuzzy this is in terms of what is the ice actually doing that invokes this. Because what it says is that coastal states have the right to adopt and enforce kind of additional jurisdiction. And this was really for the purposes of environmental protection. That's what it was drafted for. But it was in areas where the presence of ice for most of the year, which to a modeler is, what does that mean? Presence of ice, how much ice? How thick does it need to be? What does the most of the year mean? Is that 6 months? Is it 9 months? You know, I mean, we need numbers here. So that of course is constructive ambiguity, because that leaves it open for interpretation by the states that sign up to this, and that's what they're looking for. They're looking for flexibility. And then the additional language that the US negotiators included was in these areas that create exceptional hazards to navigation, and it includes a statement about paying kind of due attention to the needs of free navigation through these areas. So this was developed for environmental protection, but that is not necessarily how it's being used. So it's being used to enable, for example, Russia, who have 40% of the coastline in the Arctic, to exert enhanced jurisdiction over their part of the Northern Sea route, which they argue kind of simultaneously that they have enhanced jurisdiction because of Article 234, but by the way, they're internal waters anyway, so they're ours anyway. And so they're kind of saying two different things at once. But it all comes to fruition in this idea that they want to be able to control this route, and if nothing else, extract rent from it. So you have tariffs, you have additional needs for icebreaker escorts, which are supplied by the Russians, but you have to pay for them. You have to pay for a pilot. There are insurance requirements, and there's permitting. And so one of the operators that we were working with in Norway said, honestly, it's not the icebergs we care about, it's the icebergs of Russian paperwork. So we wanted to see if there was additional insights that we could gain from these quite dispersed climate scenarios. So what we found is that, and this is what I was noting just now, that Russia is invoking Article 234 to extend enforcement jurisdiction onto the part of the Northern Sea route that they claim. So for this, we started looking at a range of different scenarios, from, you know, aggressive mitigation efforts to business as usual. And these were all from the CMIP 5 round. Now we're doing CMIP 6. There's going to be a whole new set of scenarios. So, of course, what we found, which is what is pretty well known, is that these scenarios don't really diverge until mid-century. It kind of doesn't matter what scenario you're on for the moment, because we have this climate change commitment. You know, we're locked in to the changes that we're seeing right now. But of course, you know, there is a lot of spread in this, and the shipping season goes everywhere from 0, you know, up to 150 days, depending on the model that you're choosing. And so what we did was to estimate the likelihood with all of those scenarios. What was the probability that you would be able to get a navigation season of a month or more out of one of these scenarios? And so the very unlikely as likely as not, these are IPCC bounds. If anyone's kind of read any of those assessment reports, these are the probability bounds that are kind of standard for that. And so what it allowed us to see is, regardless of the trajectory, the probability of getting a navigable season of more than a month out of any scenario, any model, is still pretty unlikely. That you're still going to be needing icebreakers here. But if we get up into the business as usual scenarios, then that's where we start to see in the second half of the century that we're going to get routine ice-free shipping, where you're not going to need an icebreaker, and you're not even going to need an ice-strengthened vessel. And we did this calculation for every kind of polar code vessel, so that you can actually distinguish between which type of vessel you need for this navigation. This particular one is for just open water vessels, so no ice strengthening at all. But of course, the key thing here is that until you get that kind of all the ice is gone most of the time, we're still using the straits of the Arctic for a lot of this shipping, particularly if we're staying on the Northern Sea route. So this shows, this is kind of an example output from our ship routing model, which is the one that's used by industry. It's based on the Polaris, but we've tweaked it for a bit of enhanced functionality. So it gives you routes. You tell it what class, polar class vessel you want, and it will give you all of the routes that are available in any particular on any particular day, or actually a traverse is coming 9 days-ish. And so a lot of these routes, particularly, you know, in the first half of the century, are still using these straits. And so the model is kind of freely, you know, pushing all of these ships through these straits when they're going here. And then, of course, you know, we've got the archipelago, which is very complex morphologically. But if you actually look at what the climate model grids look like for those straits, they're not resolved. So this is the this is one CMIP 6 model. I think this one is CESM, but you get the same thing for any model. For this particular the Vilhitsky Strait, this looks like a peninsula to that model. So that model is not actually seeing any ice in the strait. But then what the Polaris commercial ship route model does is it throws a 25 by 25 grid over it and creates grid cells here, which it then interpolates from the ice here. But of course, all of you have seen sea ice know sea ice doesn't behave in straits the way it behaves in the open ocean. And so just because you've got a certain ice regime here doesn't mean it's going to be true here. And in fact, that ice regime is not going to make a lot of sense because it doesn't actually know that there's a strait there. So one of the things we discovered, and this was one of my graduate students, is that the commercial shipping routes were totally ignoring this. And they didn't realize that they were kind of making up ice that wasn't there. And so, so this is my student, Maria Louisa. She used a generative AI approach to train a super resolution machine learning approach to generate ice in the straits that looked like the ice in the satellite pictures. And so this is what the climate model looks like, where there's no ice in here. This is what the actual ice regime looked like. And so this is what, so then we took this and we told the generative adversarial network to generate ice, and it generated this ice. So it does a pretty good job. And so we're rerunning all of these scenarios now with what we think of as more real ice in those straits. And that's what we're working on right now. So to switch gears to snow. So this is something else we've been working on. We've been doing some work with an Indigenous Saka large animal biologist. She now lives in the US, and she's interested in the impacts of climate change on their traditional livelihoods. So Saka is in central northern Siberia, and they're traditionally reindeer herders. And then as part of some other work in CPAD, we're also working with Sami people in northern Norway. And so what we wanted to do was to look at the evolution of the snowpack and how that was influencing reindeer and what kind of policy decisions we could inform with that. And so to do that, this was another student, Emma, who implemented, it was actually originally an avalanche model that was used, it was developed in Switzerland and used for modeling the snowpack through a season in the mountains in Switzerland. And so she implemented this first in northern Norway, and now I have another student who's implementing it in Siberia. And we tested it against the snow pit measurements that we could access. And then we worked with our Indigenous collaborator and her contacts to determine the specific snow conditions that were being simulated by this model that were problematic for reindeer in terms of winter forage. So that's things like these very high density layers. So this is one snapshot from March 26th. So it's basically a line up through here. Where you have these icy layers that mostly develop if you have a rain on snow event, you'll get these icy layers, or if you get a thaw and then snowfall on top, you'll get these icy layers that the reindeer can't break through. There is also an issue if the snow is simply too deep. And so what we found is that these deep snow events, which cause problems for reindeer, are going to become less frequent in that northern Scandinavia area, but we're actually seeing that we're getting more frequent deep snow in Siberia. And the layers that are too firm or icy for the reindeer are becoming more frequent in both locations. So you're getting either the melting of the snow or rain on snow events that creates this hard pack that the reindeer can't break through. And so this is an example, this is ice incidents. And the other thing that we're working with our collaborators on was they said they could keep their reindeer alive without access to forage for 5 days. But after 5 days, they started losing animals. So 5 days was our kind of window. If it was icy for a 5-day consecutive period, then that was an incident that was going to cause reindeer mortality. And so we were tracking, again, with a multi-model ensemble, ice incidents that lasted 5 days or longer. And what we found from working with the reindeer herders is that in those conditions especially, but also in deep snow conditions, the reindeer seek forage preferentially in old growth forests because they actually eat the lichen off the trees if they can't break through the snow and eat the lichen that's under the snow. And they don't like the lichen that grows on forest plantation trees. They only like old growth trees. These are like, you know, caviar loving reindeer and stuff. It's got to be the right lichen. So, and so that makes it very interesting because if you look at, say, Sweden and Finland, they've got a lot of plantation trees. And the reindeer are not happy with foraging for lichen there. They only like the old growth forest, which is actually mostly in Norway, where they don't have such a big forestry industry. And so thinking, and this is even though Finland in particular, they've developed their forest plantations to mimic the natural ecology as much as possible. They're working really hard on this, but for whatever reason, they're not getting the lichen part right for the reindeer. So what that suggested in the policy advice where we were working with the Sami Council is that they need to provide migration corridors to old growth patches so they can get their reindeer, if there is an icy event or a deep snow event, they can get to an old growth forest. Meanwhile, the people who are doing forestry research need to think about how they can get the right kind of lichen in their plantation timbers. And so that was very direct and specific policy advice that we could provide. Now, for the Russian case, you know, we don't have that kind of direct access at the moment, but what we can do is kind of develop this knowledge in the hope that we can later deploy it. So the third one, and I'll be a bit quicker on this one. This is mostly that's been work that's being done by some students and faculty that we're working with down at George Washington University, who are part of the team. They're looking at transportation. So they're looking at bearing capacity for different types of roads under different climate scenarios that we've been developing for them. So, so they look at their all-season roads. So that's really about the bearing capacity of the underlying permafrost and how that changes over time. But of course, in the Arctic, seasonal transportation options are really critical. And so in the winter, you have ice roads, which often cross water bodies. So you really need to know about the ice thickness on those roads. And then over land, we need to think about what the snow depth is. So we have winter travel over ice roads and snowpack, as well as the all-season roads where we're really only worrying about the permafrost bearing capacity. And so Kat, the student who worked on this part, did an assessment of the costs, the travel costs, for different scenarios. And so I'm just showing here the low emissions and the high emission scenarios. And where it's red, the travel costs are increasing over the 21st century. And where it's blue, it's decreasing. And it's really only these small areas here, which is interesting because this is also the Sakha Republic where I was just showing you with the reindeer. It's right here. So the travel costs are increasing, but the part that we really wanted to get into is, are there going to be remote communities that actually become inaccessible? Because that becomes a really key issue. This isn't like Greenland. With Greenland, all of those coastal communities are supplied by ship. And so, you know, what accessibility for these communities is really a maritime question. But if we're thinking about accessibility for these communities, particularly in Indigenous lands, we need to have terrestrial transport. And so one of the things that Kat looked at then was, what are the settlements that are likely to become inaccessible because of problems with particularly with the permafrost bearing capacity? And what she found was that it's less of a problem in the low emission scenarios, but in the high emission scenarios, she found that 40 settlements were highly likely, with that probability rubric, highly likely to become inaccessible by mid-century. And so that was something, again, where she was working in particular, in this case, she was working in particular in some communities in Canada, talking about accessibility options for those groups. They were also working some with Russia, but that's not happening right now. So then we started to think about what all of this means for the Arctic as a whole, because we had this idea when we started this project that there were all of these different pressures on these different communities that were being kind of prompted by climate change, but a whole lot of other change as well. And where you have pressures converging, you need to have a response. And so what would that look like? And what became very clear to us was that there are actually many different Arctics. And you know, one of my collaborators, she's always fond of saying, if you've been to one place in the Arctic, you've been to one place in the Arctic. And that's really true as we start to get into particularly these questions of accessibility and use of the landscape or the ocean, is that while the large scale signals are all kind of in the same direction and very clear, how the particular situation responds to that change is quite different. And so we developed a set based on interviews with different communities in different areas. And we have an advisory board that comes in and helps us. We started creating scenarios. And I know you like building future scenarios. We started creating scenarios or storylines for different ways that a particular place might respond to the pressures. So, you know, there's resilient communities that they're going to invest in sustainability, or, you know, there's one that was very popular for a time, this idea of Silicon Valley North, that it's cold and so you don't have cooling costs for these big server farms, and so they could do that. Or you could just kind of go for broke and have heavy increase in extractive industries. So there were all sorts of different scenarios. And all of these, including this idea of geostrategic spill, or the idea that there would be tensions from elsewhere on the planet affecting development in the Arctic, that was developed before Russia invaded Ukraine. So it was already on the horizon that things could get interesting. So we have those possible pathways. And of course, those pathways depend on not just on the vision of a particular community and the resources that they have access to, whether it be skills in the community or rare earths or fish, but also their capacities. And so the other thing that we did with this was to map the various capacities that might be drawn upon. And so this is an example of the kind of mapping that we were doing. This is a confluence of transportation accessibility, so ports, aviation, and roads and rail. We did this also with, say, hospitals and healthcare facilities and other things like that. So we needed to take into account the aspirations, the resources, but also the capacity to make good on what those options were. And so, like all climate models, all development scenarios are wrong, but some are useful. And in fact, what we found working with our with our partners, our advisory board and the various operators we were talking with, just the process of exploring these scenarios turned out to be really useful for them based on what they said. And so this was the idea, and again, I'm emphasising this is pre the war in Ukraine, and so that tends to put the Barents area in one, but of course, you know, there's a halvish line here now. Although the fishing fleets are still going back and forth, but there is a halvish line here now, and so we may not have grouped the Barents in that way now, compared to what we did then. But in general, so the current expectation, for example, for this Barents area was that this was going to be a very sustainable, very green, kind of focused more on industries like tourism. But then when we explored departures from that scenario, one of them, which was a very strong aspiration, particularly in northern Norway, was this idea of becoming Silicon Valley North. But it was also acknowledged that this would be an area where geostrategic still could happen. And in fact, this is the departure we're on right now for this region. And for Siberia, the expectation was they would keep mining non-renewables, but perhaps there were these different departures. One of those is just that, you know, permafrost thaws and it becomes a massive source of methane. We have the Bering Beaufort and then the kind of Nunavut Greenland. So at the time we did this, we split it into 4, but I think we're now starting to think about splitting this into even six different regions. And so, yeah, so I think with that, I will stop. So I'm at the end of my class.